もしやコスモでは。
Cosmo makes me free.
Cosmo AP Luxury Sports.
Yep, it's part 49 of my 76 Mazda Cosmo Restoration. The last two episodes were spent retrofitting modern electronics into the 70s instrument cluster. And I'm going to start with the last gauge that I worked on, which was the temperature and fuel gauge. This gauge is run by two stepper motors and will need backlighting. So the first thing is to build a circuit board to mount the motors and the backlights. Now recall that I already created the board mounting pattern in episode 48, so now we just need to add the components. I like to start with all the connectors in this case. So I'm going to use some Molex 90-degree board connectors. And notice that I'm working on the top copper level because the motors are actually going to be below the board, so I'm going to be soldering on the top, which makes it really handy because I'm going to have to use some surface mount parts. I'm going to do about 1.5 millimeter traces. That should be about the maximum size that we'll be able to fit on the connector here. And I like to run my traces in 90-degree increments. So 1, and then 2. Oops. And we're going to have to be a bit careful here because I need to leave room for the backlight LED. Okay, and well, now we'll do the exact same thing on the other side. Now the nice thing is, afterwards I can go in and rearrange these traces if necessary to make them a little bit more symmetrical. I spent a little bit of time off camera straightening these traces and also making them just a little bit smaller. Time to start placing some LEDs. I need to place an LED in the center for the warning light, and then probably one at the bottom, one at the top, one in the middle to backlight the gauge face. Okay, we're going to need one right about here. That orientation. Actually, we can move this down a little bit. Awesome. Another one in the center. Here's where we have to get creative. I'm going to have to place an LED roughly in the center right here so that I can light the gauge graduations here. Yeah. These holes are for this little bump out on the motor, which as far as I can tell, because I've already cut this one off, it's just a little plastic guide, so we don't actually need them. Now I have freed a bit more room for this LED. It's just a matter of figuring out how I can orient it. And to make matters a little bit more annoying, each one of these LEDs requires a 0.1 microfarad capacitor across power supply and ground. So that means I also have to figure out where to put 4 capacitors. Now thankfully, I'm going to do this in surface mount. It's going to be a pain to solder, but it might make it a little bit easier for me to place these capacitors. It's going to be brutal. I reserve the right to change the position of these capacitors when I find out that I can't run any traces. Well, after staring at this mess for about 20 minutes, I ended up rotating these 3 middle LEDs so that supply voltage and grounds are at the same side and the capacitors can uniformly go above them. So these LEDs work on a data bus. That's why you can control thousands of them with just 3 wires. Which means that the data out of one LED needs to be routed to the data in of the next LED and so forth. So not only do I have to run the power wires, but I also have to figure out how to get these data wires through. And I think what I will do is send each data wire up through the capacitor, which might make it a real joy to solder. And someone's going to say, yes, this would be a lot easier if I was to do a multi-level board. However, I'm making only one of these, like, ever, so I just don't see the point in designing a multi-level board and having it sent out to be fabbed. I'll do that for some of the other boards. Here, move this up here. Just going to roughly position these traces for now. I'll properly clean them up a bit later. Put that ground there. With all the traces in place, I can do a virtual continuity chest. A continuity chest? Really? Is that like when they're filming like a sex scene in a movie and they have a body double and they just have to make sure the boobs look the same? Okay. With everything connected by traces, I can do a virtual continuity test and just make sure that everything is connected the way it should be. So we'll first check the power supply, that it goes to all of the VCC connections on the LEDs, which it does. And of course the capacitors, one side of each capacitor, which they do. The same with ground. Connects to the ground on each LED, and the opposite side of each capacitor. Ground, 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 yes. Data in goes from one LED to the data out, and the data in, and the data out, and the data in, and the data out, and the data in, and the data out, which connects to this pad, which then goes to the data in, which goes to the data out, which goes to the last connection on the connector. Sweet! Now I just have to make these traces look less like a hairball and more like a well laid out circuit board. I've probably mentioned before that I like straight traces, so I'm just going to start straightening these traces. This will take a little while. Some of them you can't get absolutely perfectly straight because they just need to go at an angle. But copper connection does a pretty good job at trying to reorient and keep everything straight when you change the angles. Put that in the middle of that. Okay, well, I probably have about another hour of that to do, so turn the camera off once again and come back to it when it's done. Just move these up here. Don't want to end up too close. That's probably good. That one's straight. Put the silk screen back on. That board is done. Really, my only concern is that these LEDs fit where I want them. And it looks like they do. Now, you've all seen me use the toner transfer process before to make printed circuit boards. So that's what I'm doing now. I've ran a few print jobs through the printer to make sure it's nice and warm, because I've always found that to be helpful in using this paper. Give that a print. Now, as always, I have the resolution set as high as possible and the toner density set as dark as possible. And I always put multiples of the same board on the page, just in case I need to attempt etching again for a second try. Yeah, not bad at all. Now this is just a piece of single-sided 1-ounce copper circuit board. It happened to be the right size. It's been sitting around a little while, so clean it up nice with the Scotch-Brite. Now the pattern just goes onto the copper. Carefully send that through the laminator. Oh, there we go. It's kind of stuck in there because it's not long enough to pull it out. This, by the way, violates the warranty of your laminator. It's one, and then I always like to send it through a second time. I don't think that worked at all. Maybe it did. Now into the water for a few minutes to release the paper. Now yes, there's some tape on that, and that is because off camera I accidentally bumped into it in the water, tore my first attempt to pieces, so I did another one, and beautiful. That bolt hole, but who cares? Now the laminator I'm using right now isn't actually as good as the one I normally use, but I couldn't find the one at the office on Friday, so had to go with that one. And I like to etch my circuit boards with ferric chloride. This is nasty stuff. It's very corrosive, yet it's never actually bothered my skin, so really the only reason I'm wearing the gloves is because of the staining. This stuff has been the ruin of many of my clothes. The shop microwave is only ever used for warming up ferric chloride. Stuff works a lot better when it's warm. Of course, I'd like to point out that a material safety data sheet specifically says, do not warm in microwave. Dangerously heated chlorine compound. And in goes the board. I now have between 5 and 10 minutes of doing this. Took a bit longer than I thought to etch. I guess my ferric chloride is wearing out. A little bit of water to stop the acid. Yeah, that's not bad. Pretty damn good. The tack and the speedometer have a lot more space underneath the gauge, which means that I can simply make a circuit board which covers this entire area by using these pre-made WS2812B LED modules. These include the LED itself and the little 0.01 microfarad capacitor. Turns out that the shape of the tack is the shape of the board I need to make. The easiest way to get that onto the computer is to simply scan it. Well, now I just need to turn the scanned gauge face into an outline for the board. Start by converting it to black and white. Then what we'll do is we'll take a copy of that and reduce the size of the copy to 99%, let's say. A barely perceivable change. Then invert the image. Magic wand tool to grab the outline. Copy that. And paste it as a new selection. And then just center it within the other one. Perfect. Let's merge all of those layers. Then just a matter of using the eraser to clean it up a little bit. Okay, all cleaned up. That is a pretty good outline of the gauge face. Through a little bit of experimentation, I have already found out that I need to reduce it by 50% to end up as the right size. Existing board. I'm going to import an image and select the image. Perfect. Convert that to a layer. Top silk. Oops. Convert that to a polygon, which gives us the outline, and then flip it to the board edge. And just like magic, we now have a board in the shape of the gauge face. Just center that up. And now I can place the LEDs. Unlike the last board for the fuel and temperature gauge, this board I have a lot of room to work. So what I'm going to do is use these LED modules instead of the raw surface mount LED. Honestly, a lot easier to solder. Now the procedure to design this board is exactly the same as the other, except I'm using the modules instead. So what I'm going to do is turn off the camera, do the board, because you just saw me do a board, and then we'll come back to it when it's done. Well, and after a few hours of designing boards, we have two that look remarkably similar, because basically they do the same thing. On the left is the backlight board for the speedometer, and on the right, the backlight board for the tachometer. Basically, they're the same thing. They're just stringing together these WS2812B modules together in series, connecting the powers and grounds together, as well as the data in to the data out to the data in to the data out, all along the circle, and ending up at a header where a connector will be mounted. So with all those boards designed, I guess it's time to make them. Perfect. Nice. Now I just have a bunch of tiny holes to drill. So I will get everything mounted. Insert joke here. I don't know what that noise is. Yeah, it looks like this board is going to need just a little bit of adjustment to fit. Kind of figured that would be the case. Just make a few marks. And make a few minor adjustments with the Dremel. Perfect. I always leave the toner on as long as possible to protect the copper. That way when I'm drilling and cutting and sanding, I don't mess it up too much. A little bit of acetone removes it. And that actually was a pretty good etch. I don't see any pitting. And now it's time to solder. As you recall, the speedometer and backlight boards will use these addressable LED modules. And the way I'm going to solder all of these on is to just use a little bit of copper wire in place of the header pins that are meant to be installed. And that way they lay flat on the board. Now the only thing I have to pay attention to is the orientation of the module, because some of them are flipped in order to make the traces easier. So what we'll do is first now this first one I'm going to keep the wires a tad bit long because it's going to make it easier to test. I think the trick is going to be to solder this diagonally so that all the holes remain lined up. Now, because these holes don't quite line up, I'm going to have to use the flexibility of the wire to sort of force these in place. And that kind of sucks because I have to do that 1, 2, 3, 4, 5, 6, 14 times. Well, now I just have to do that a bunch more times. Well, I'm back again at Corey Auto Wreckers. This time I'm on the hunt for some gauge needles. And wouldn't you know it, this is a BMW 328i, which is the same car that I got my seats from. I think this is the exact same car. Geez, maybe I should have just bought a BMW. Well, that came out really easily. Just 2 screws, 1 connection, slid right out. Almost wasn't worth filming. Well, with both boards soldered up, I've kind of jury-rigged everything together with jumper cables because I haven't yet received my connectors. So I just loaded an Arduino Nano with the fast LED demo sketch, and here we go. One of my connections is a little loose. There we go. Sweet. Ooh, shiny. Now here's where the fun begins because these are the LEDs and these are the capacitors that need to be installed on this board. So I recently did another electronics project involving surface mount parts. And well, you can use a regular soldering iron to solder them with a few tricks. Realistically, the way to do this and not drive yourself batshit insane is to use a hot air soldering station. Now, when using hot air, you use soldering paste typically instead of soldering wire. It's just a matter of putting a little bit of paste, it's actually on the pad where each component is going to go. And then popping on the component. Nice thing is that the paste will mostly hold it in place. Now these pads are a little bit bigger than they need to be because I was considering hand soldering it. And the rest are done the same way. Man, this needle looks a little bit familiar. Thankfully, as far as surface mount parts go, these are actually pretty large, so I don't yet have to break out the magnifying lamp. Okay, now just place the components. Now theoretically, when the solder is heated up and the flux melts, the components sort of self-center. They don't have to be exactly perfect. I'm just hoping that it works as well without a solder mask as it does with a solder mask. And the WS2812 LEDs, paying attention to the location of pin 1 as marked by the little notch on the case. Now, one final check before I solder this thing, because removing parts is a bigger pain in the ass than installing them. Yep, all of those look like they're in the right spot. Now, the hot air station works by blasting out, well, hot air to heat the board and the component, at the same time liquefying the solder paste and soldering everything together. When you're good at this, you can solder the entire board in one go. So we'll see how good I am.
You know that magic moment when the solder paste flux and everything melts and then reflows? Shit, want that. That should be okay. When you get a good preheat going, you can move from one component to the next. And I say this as if I'm an expert, because this is like the third time I've ever done this. Fascinating to watch, though. And this is how it's done in manufacturing, except all the components are placed by robots, and everything is soldered together in a reflow oven instead. And incidentally, oops, I spoke that. And incidentally, you can make your own reflow oven using a toaster oven and a modified thermostat, and that is on my list of things to do, eventually. I have to touch this one up.
These steppers have these tiny little nubbins right here that need to come off. As far as I can tell, they're just for manufacturing purposes. Just no mechanics in them at all. And then that goes into the board. Let's see how well I drilled these holes. Ooh, looks like pretty good. Look at that. And they just solder right in place. And now just have to test the LEDs. Arduino Nano loaded up with the fast LED sketch, and if I can wrangle the wires, get in there, which is of course what she said. There we are. And the data pin. Alrighty, looks like it's working. The astute viewer may notice that this board is curiously not the one I filmed soldering. Well, that's because I screwed up. And this board was actually attempt number 3. Attempt number 1, all of the LEDs but the one on the left worked. And what I found was that the leftmost LED was sitting really weird on the solder pad. So after some attempts to fix it, I figured I may have just buggered the whole thing, so I gave up and etched attempt number 2. This time I increased the size of the solder pads for the left LED, and yet it didn't work. And I realized what I did. When I was designing the board, in order to position the left LED, I accidentally flipped it instead of rotating it. Now, if you think about that for a sec, because it took me a minute to realize that when you flip something, you mirror it. Well, this is a polarized component. All of these pins do different things. You can't just mirror it. You have to rotate it so that all the pins stay where they're supposed to go. So, attempt number 3, I rotated the LED, and wouldn't you know it, it works. And that's the last bit of fab work needed on the cluster itself. Next, of course, are the control electronics, but before I do that, just review what I need to control. There's one stepper motor for the tach, one stepper motor, and 2 screens that use the SPI bus for the speedometer, 2 stepper motors for the temperature and fuel gauge, one Nextion screen for the auxiliary display, which uses a serial interface, a backlight board for the speedometer, which uses WS2812 LEDs, and a backlight board for the tach using the same LEDs. Each of these boards require one data channel for the LEDs. Additionally, 5 WS2812 LEDs to backlight the temperature and fuel gauge board. Oh, and let's not forget the Rotary encoder on the bezel. I've put a lot of thought into how I'm going to control that stuff, with the requirements being CAN bus to interface with the Megasquirt, enough I/O to control all the screens and steppers, enough memory to control the program, and the ability to integrate it into a package that will fit behind the dashboard. CAN bus requirement is easy, the MCP2515 chipset. And we have the Arduino Uno, the Arduino Nano, the STM32 Blue Pill, and a variety of ESP8266s and the ESP32. Now with all those screens, the Atmega 328 base boards just really don't have enough memory or speed. STM32 is powerful, plenty of memory, and has built-in CAN bus. Yeah, unfortunately the Arduino libraries don't seem to support the built-in CAN bus, and I'm just not going to learn another framework to program this thing. ESP8266 in all its forms, plenty of speed, plenty of memory, no CAN bus, but 3.3 volt logic, and I don't need the Wi-Fi functions for anything, so I'm not going to do that. ESP32, much more powerful version, dual core, basically runs a real-time operating system, kind of overkill, kind of huge, again 3.3 volt, don't need the Wi-Fi. So what I've decided to do is use this. The Atmel Atmega 1284. The 1284 is kind of an overlooked processor in the Atmega line that I've used in several projects. It's quite capable, and in a small package. 128K of flash memory, 4K of EEPROM, 16K RAM, 32 general purpose I/O lines, 2 UARTs, I2C, I2C, SPI, and a bunch of other stuff. Easily enough power to run all those screens, stepper motors, and CAN interface. So what I'm going to do is design a custom control board that has all of the I/O that I need. And I'm going to do things a little differently. Normally I would etch these boards myself, but in this case, because I want to be able to do a lot of surface mount stuff, double-sided boards with the proper solder mask and all that good stuff, I'm going to have them fabbed by PCBWay. And what does this mean? It means I gotta spend some time on the computer. Hey Google, please turn on the shop computer.
Sure, turning the shop computer on.
God, I hope I just triggered everybody's computers to come on.